TuckTech, units of measure. We call the quantities like length, time, mass, and temperature dimensions. We can measure them and they have a value. In terms of a particular system of dimensions, there are two groups: primary dimensions like length and time, mass and temperature, and secondary dimensions like area, speed, force, flow rate, all made up from the combinations of primary dimensions, as we'll see in a moment. Units are the names that we've chosen to call the primary dimensions, and standards have been established so that we can all know what we're talking about. For example, the primary dimensions of length can have the units of feet, or inches, or meters, or so on. Any valid equation that relates physical quantities must be homogeneous, or homogeneous. Each term of the equation must have the same dimensions. For example, 3 inches plus 8 inches equals 11 inches. That makes perfect sense. What doesn't make sense is 3 inches plus 8 seconds equals 11 degrees. Seems obvious, but if you don't watch for this, it will sneak up on you, and you might even crash a spaceship into Mars. There are basically 3 systems of units in use today: the SI system, which is commonly called the metric system, the British system, and the English engineering system. Wait a minute, I thought the Brits were English. Well, they are. Kinda. The SI system uses mass, length, time, and temperature as primary dimensions. Mass is measured in kilograms, length is measured in meters, time in seconds, and temperature in Kelvin. Then the secondary dimensions are made from all of these. Other secondary dimensions can be found by using the primary dimensions and Newton's second law, which states that force equals mass times acceleration. In the SI system, force has the units of newtons. Now we know where they came up with that. So F equals ma becomes, by definition, 1 newton equals 1 kilogram times 1 meter per second squared. What about the British system? Well, the British system has the primary dimensions of force, length, time, and temperature. Force is measured in pounds, length is measured in feet, time is measured in seconds, which is something we can all agree upon, and temperature is measured in Rankine. Since mass is a secondary dimension, we can use Newton's second law to define it. We start with F equals ma, then we solve for m to get m equals F divided by a. So we have 1 unit of mass equals 1 pound force divided by a foot per second squared. So now we need to come up with a clever name for the unit of mass. I know, let's call it the slug. Really, that's what it's called. It's a slug. So 1 slug is equal to 1 pound force divided by a foot per second squared. I bet the English engineering system can do much better than that. Let's take a look. The unit of force is still the pound force, length is still the foot, time is a second, temperature still measured in Rankine, but mass is measured in pounds. Wait a minute, I thought force was measured in pounds. Well, it is. There's a pound force and a pound mass. Handy, right? 1 pound force is the force that gives 1 pound mass an acceleration equal to the acceleration of gravity. The acceleration of gravity is defined as 32.17 feet per second squared. Remember when we did this for the SI system, the Newton was created or defined from the other primary dimensions. Since in the English system, the pound mass was selected as a primary dimension, we run into a bit of a problem with Newton's second law. To avoid this, we introduced the constant of proportionality. This keeps the equation homogeneous. G sub c is defined as 32.17 feet times pound mass divided by pounds force times second squared. So 1 pound force equals 1 pound mass times 32.17 feet per second squared, all divided by G sub c. Let's see if this is homogeneous. Using our dimensional analysis, we can verify that it is indeed homogeneous. We want to know if the left-hand side of the equation is the same as the right-hand side of the equation. Leaving the left-hand side alone for now, let's divide the numerator and the denominator of the right-hand side by 32.17. Since we divide both the numerator and the denominator by the same thing, we haven't changed anything at all. Everything's still equal. You can probably see what's going to happen here. The pounds mass will cancel since there's one in the numerator and one in the denominator, as well as the feet and the second squared, though that one's not quite as obvious, but it does work. This leaves us with 1 pound force equals 1 over 1 pound force, which if we multiply the numerator and the denominator both by 1 pound force, we get 1 pound force equals 1 pound force. This is definitely homogeneous and equal, which is what we wanted to show. Wow, that was a whole lot of work just to avoid saying the word slug. Yeah, it is. So of the three systems of units and dimensions that we've seen today, the one that's the most trouble-free is the SI system. It's the most widely used in the scientific work throughout all the world. So let's just all use that. I'm sure the United States will convert to the metric system soon. And it's been true for over 40 years. There's just too much that has to change for that to happen. For example, what size is a sheet of paper? Why, it's 8.5 by 11. When we pull up and order a quarter pounder at McDonald's, should we order the 0.453 kilo burger instead? It's everywhere. So living in America, you're going to need to know how to convert. That's where the dimensional analysis comes in, as we'll see in future TuckTechs. So the advice of the day is to 1, keep your equations homogeneous. So always write down the dimensions as you are solving a problem. And 2, if you don't want to worry about the whole G sub C constant of proportionality, then convert your problem into the SI world, solve the problem, then convert your answer back into the world you live in. If you have any comments about this TuckTech or ideas for future TuckTechs, please feel free to contact us at info@ashtuck.com. TuckTech.